this is just quickly to talk about platforms and ways to collect the data, and then to talk a little bit more about some of these issues of artifacts and errors and ground control and some of those things. So we'll go through this. There's also a whole bunch of examples at the back end of the slide set that I'm not going to show you, but just various kind of scientific applications of SfM and what some of the models look like and other things. So there's a ton of back that we've loaded into this, and it's worth touring through on your own. So we talked a fair amount about airborne platforms to collect these kinds of data. So there's quadcopter type things, the DJI of the world. There's these like super high-end helicopter type platforms, single rotors, that sometimes approach the FAA 55-pound weight limit to be a small UAS. Ramon mentioned things like autokites and fixed wing systems. So a colleague of Chelsea and I's, Mike Bunz, who's at Utah Valley University, has done a lot of work with a thing called an EV, which is a fixed wing system. And he's flown some very long stretches of the San Andreas Fault and other sort of fault type features with a fixed wing. We cover a lot more ground with fixed wing. The kind of helicopter type platforms have their advantages basically being that they can take off in high wind, take off and land anywhere, basically on a small footprint. You can catch them with your hand as they're landing. They're relatively easy to fly. They're also quite cheap. The downsides are that they take some training to fly. There are certain rules about how you operate them, so I'll talk a little bit about FAA rules in a second, but some of you know more about this probably than even Chelsea and I do, because you've already got your FAA 107 and I've done some flying. But that's sort of the helicopter world. This is what most people that I interact with are flying, are these DJI Phantoms or Matrice type systems that cost a couple $1,000. It's quite affordable. Some of these things are really quite small these days, which is nice. So you can stick them in a backpack. So fixed wings, by comparison to the multi-rotors, are that they are relatively easy to fly. They typically have longer flight durations, so you can collect more imagery. You can stay up in the air longer. They are essentially crash landing, though. A lot of the systems, like the EV, essentially belly flops onto the ground, and it can be quite damaging if you landed in the wrong place. And so that's another disadvantage to these. But for larger scale mapping efforts, the fixed wings are really quite nice. And I think the EB is sort of like the one that a lot of people are using. It's a turnkey system. It's also relatively expensive. I think it's like $15,000 or something. So quite a bit more than just going out and buying a Phantom 4 system, multi-rotor system. Balloons, we talked a little bit about already. I've been out in the field with Chelsea using a balloon. Ed Nissen, who's some of the slides that we showed at the beginning that Ramon showed, has done a lot of work with one of these Alsop helikites. They're nice because they are tethered, and so therefore they're exempt from FAA regulations. So you can potentially use them in different places than you can with a UAS. They do require helium, which can be a challenge to source and requires you to haul around a big helium tank. But they're different levels of these things. You can do this with just like a really cheap kind of balloon that they use at like a car dealership to lift up a banner or something like that. Those are quite cheap. I know Ramon's flown some like hundreds of dollars of balloons. But there's also these more sophisticated balloon systems. So that's another option. They can stay up for basically as long as the helium lasts, so you can put them up there for a long time. You can carry relatively large, like SLR type cameras on them, which you may not easily do with a small multi-rotor system. And they use the Picave thing, which is basically a way to keep the camera oriented. So that's what in this woman's hand here is the big spool of line that allows you to feed the balloon out, and then with the camera on it to keep the camera pointed straight down as the balloon tends to rock. So this is not something we see too many people using now that UAS systems have become quite affordable and easy to use, but it's definitely worth thinking about as an alternative, especially if you're working in wilderness areas or other places that are virtually impossible to fly the UAS. So that's another couple of pictures of what these things look like. We talked a little bit about historical aerial photography, and so this is an example of the Landers fault scarp, which is the Landers earthquake from 1992. So 85 kilometers of aerial photography, 30, and results in a 30 centimeter resolution DEM. So this is a case where you get where archival photo works really well, as I've said, I think previously. Sometimes this works really well, but other times it doesn't. And it's really all about the collection geometry of the imagery. And so this is a little bit of a trial and error kind of thing. The other challenge with these is that they can be very hard to geo-reference, right? Because there's no ground control. Nobody when this imagery is collected, there's nobody out there putting out ground control. So sometimes you can get lucky and figure out like if there's a man-made feature in the imagery, like the intersection of two roads or some other thing you can identify, you could go out into the field and GPS that coordinate and then use that to georeference your data. Or you can pluck coordinates from, say, like Google Earth. Like you can go in and figure out what the lat long of that position is in Google Earth and use that as a coordinate to georeference these. But this is generally works well to produce nice. If it works, you produce these nice models, but their overall positioning is not particularly good. So if you want to use them for like multi-temporal analysis, it can get more challenging. But this is definitely, there's a huge archive of aerial imagery out there from various sources. And so I think actually in some ways this is perhaps an underutilized pathway, but there are definitely people doing this, but you can imagine going back and digging through old aerial photographs and building models. In terms of the UAS data collection, there's all these different apps now that make it pretty easy to do this. So a lot of the airborne collections now for SfM from a drone are done programmatically. So you basically use a tool like Drone Deploy or Pix4D, or there are these various tools. And so you essentially program your flight lines, you push the flight plan to your UAS system and you hit go and it takes off and it flies the pattern and it comes back and then lands. This is sort of more foolproof than trying to fly yourself. People still do that when you take off and use the joystick and controller. But in general, that's not what I would recommend. I'd recommend getting one of these apps and then using the app to program. You can also set your overlap and things like that, which is Chelsea talked about this already. So that's just the way we recommend doing this. Again, the specifics we're not going to get into here because it's very much about what drone you're using and what your plans are. A question was asked earlier in the chat, which we didn't talk about, was kind of some of the new systems have RTK positioning on board the drone. So this is some of the newer DJI systems you can buy with an RTK, so you get a base station. There's also aftermarket systems where you can buy like a Septentrial UAS RTK board and put it on your drone and DIY your direct georeferencing. The advantage to this is that putting out ground control can be quite labor intensive, especially if you're working in a challenging landscape. So having to run around and put out some kind of visible target that you survey with a GPS unit actually ends up being a good chunk of the time spent in the field. So if you can direct georeference the positions of the camera every time the shutter clicks, that can be quite powerful. It allows you to fly much larger areas without having to do that ground control surveying. So, and Chelsea, you've done some direct georeference work recently, right? Do you want to comment on that experience?
Yeah, so it's, I've done the ground-based work, which is, we've said earlier today, is very, very labor intensive, but then also putting post-processing GPS that with an EB that can talk to a ground-based GPS. And that two benefits: one, it takes much, much, much less time. And two, because each photo has a very high quality georeferencing position, it is then much better than any sort of ground-based ground control that you can do. So it's more expensive, but especially if you're doing topographic differencing and you really need well georeferenced data, if you can afford it, that's what I would recommend.
Right, and that's these are more expensive. So some of these systems that have RTK integrated cost more because, as we talked about at the very beginning, it's actually the high precision GNSS system is actually the most expensive part of this whole thing. So you're paying for that potentially depending on which system you're buying. So other things that just to touch on here because they've come up in conversation. So if you're going to go out and do this, you basically need to be FAA Part 107 Remote Pilot and Command certified. And so this is essentially a test you take every couple of years. There are trainings you can sign up for, both online or in person. They don't test you on how to fly the actual UAS. They test you on sort of airspace regulations and other kinds of practical considerations. But this is just within the FAA space. So then on top of that, there are local regulations. So, things like national parks and state parks and other areas have rules about what you can and can't fly, or when you can and can't fly. And then on top of that, your institution may have rules about what it requires for you to fly. So your university or your employer may have additional rules. So this can be a bit of a labyrinth. And certainly if you're working outside the United States, the rules and regulations vary by country. So being aware of that, I recommend showing up in some country you're not familiar with and launching your drone without doing a whole bunch of homework. So these are just practical considerations. The other thing that you need to have is actually you need to have your UAS registered with the FAA. So here's one of Ramon's UAS certificates of registration. This is something you do through the FAA website, but you basically have to register your tail number of the platform. So a lot of these rules are carried over from FAA aircraft regulations. Right? And Chelsea added this is important. So UAS use with students. So there's a whole set of FAA guidelines about if you want to fly with students. And I won't go through all of this here, but essentially the academics are not considered hobbyist users. And so if you're using this for research or teaching, you really should be FAA certified. There are rules about whether students themselves do not need FAA Part 107, as I understand it, as long as there's somebody in command who is.
Okay, so that's kind of just basics about some of the platforms. The other thing I didn't talk about, what you all are going to do at lunch though, is we talked about aerial platforms primarily, but this works quite well with handheld cameras or cameras on a pole. So if you want to take photographs of, say, a bigger outcrop, you need to position the camera at different places. Putting your camera on a little like telescoping painter's pole or something like that works quite well. It's also handy if you're looking at rock outcrops or paleontological sites or something where the outcrops are kind of planar on the ground but are relatively small, and you don't want to get a UAS out, or you don't have the ability to do so. A camera on a pole actually works pretty well for those scenarios, or just walking around with a camera in your hand and taking pictures of an outcrop. And that's basically what most of you will do at lunch, hopefully, is go outside your house or your office or go find something and take pictures of it. So here's a little bit of discussion about acquisition geometry and some other issues. So there are three examples here. There's like nadir looking imagery collection, divergent, which is basically you stand in one spot and turn. And then there's convergent imagery collection. You're going to get your best results with a kind of convergent example. Nadir looking works pretty well if there's a lot of overlap. That's essentially the UAS collection example. Although that example we showed you from Farleone, where Ramon collected, he flew in a circle with sort of oblique collection, right? So that's more of a convergent collection geometry. The thing you definitely don't want to do is go stand in one spot and turn and take a bunch of pictures. So this is does not result in good collection geometry, and this will fail. So if you do this at lunch, you probably will not get great results. So I really encourage you to think about this like moving in an arc around whatever you're taking pictures of. Move your feet as you take pictures will result in the best result in general. The divergent geometry, people ask this sometimes, many of you may be familiar with gigapans, which is this tool for taking super high resolution imagery. It's used for outcrop geology and things like that. The gigapan is essentially a divergent geometry. The camera stays in one place and the camera turns. And so know some people have tried to use gigapan imagery for SfM, and it doesn't generally work very well because it's the wrong kind of acquisition geometry. So that there's that. So this is what this looks like, and basically notice that there's two lines of camera positions. There's one up higher or further away from the target, and then there's some closer. So this is, again, applies to if you're shooting with your hand, or if you're flying a balloon, or you're flying a UAS, that flying potentially or collecting at different distances from your targets actually makes good sense, and potentially also incorporating some non kind of nadir type shots. So basically oblique images are all good practice. So like put these in your mind for when you go out at lunch here and take some pictures. And so you want to try to take several ranges and move in this kind of arc around the target. In terms of cameras, turns out lots of things work. You can make a really nice model with your iPhone or whatever, Galaxy S3 or whatever phone you're carrying around that has a camera built into it, or you can get much fancier and use a larger SLR type camera. Generally, the better the camera, the fewer issues you're going to have with the radial distortion of the images. And I'll show you what some examples look like in a second. There's also like fixed focal lengths are generally good. So trying to, like a prime lens, like a 20 or 20 millimeter prime lens is usually a good choice as opposed to a variable lens camera where you're changing the range. The settings, this works with GoPros, but generally are not as good as, say, a better camera with less fisheye type view. And then, as we talked about, the higher the megapixel of the camera, the higher resolution of the sensor, the larger your images are going to be and the longer your run times are going to be. So, going out with some super high-end SLR may be appropriate for certain things, but may also just lead to very, very large images that slow down your processing. If you're using a UAS system these days, a lot of the times the UASs come with cameras integrated, so you're sort of stuck with those, especially at the lower end of the spectrum of cost, until you get up into like bigger systems where you have interchangeable payloads. You're kind of stuck with whatever the camera is on board. If you're flying a balloon, you can tether whatever you want to your balloon. So again, a lot of flexibility in cameras. I don't know if Ramon or Chelsea, I see Ramon's back, want to comment on your camera experiences in particular.
I'll just say one thing that, I may not see this that clearly, but one issue with a couple of issues with the cameras. One is of course, lens quality. Second one is that we always want to have a fixed length. So you don't do zooming, you always just keep it one, because that will really confuse meta shape. And then the third point in terms of camera quality is basically the more you get to the full frame CCD imaging, the better the quality. So imagine, if you have the smaller the chip, the smaller the sensors are. So even though you have a 20 megapixel picture, it might be going into only 10 mega sensors on the CCD. And so it's better. And so there's a lot of interpolation basically that has to be done. And so the actual image quality is slightly lower as opposed to the full frame, sometimes people say, which means that you're getting 20 megapixels on a 20 mega sensor CCD in the back of the camera. And that actually makes a difference in detail with the SIFT kind of really finding those matching points. So that's why a lot of times you see in the drones, CCD is it's the imaging plane of a digital camera. And I forgot what it means. Charge coupled device. Yeah, so it's what, instead of film, what you're measuring in the back of your digital camera. And so so the fancier the camera in that sense, the higher the quality of the lens and the imaging plane, the possibly better performance you'll get. So we see that in the UASs, like in the DJI group of products, the sort of, as you go up in capability, one of the things you're going up is in camera quality. And then maybe Chelsea, if she wants to comment.
Very quickly, less technical, but be sure to clean your lens every couple of flights, because otherwise that can really mess up whatever nice quality camera you have.
Good point. So this lens distortion thing. So there are one of the common things that happens is you basically get a distortion of the image as a function of the lens. And so there's barrel distortion and pin cut cushion distortion. Some of you are all probably familiar with this. And so this shows up in various various SfM models. And so there's this good paper, James and Robinson, you may recognize these guys from previous references. They've done a lot of the early work on SfM especially for geoscience applications. And so this paper is really good, this mitigating systematic errors in topographic models derived from UAV and ground-based image networks and Earth surface processes and landforms. So this is a paper that definitely is, and these figures come from this, but basically they talk about these sources of these errors, but then also how you potentially mitigate them. And so there's this kind of doming that's quite common that you see in these models, and it's driven by this lens distortion. And so they basically talk about how you mitigate it, which can be, there's lots of different ways to mitigate this, but one is to incorporate oblique camera positions. So in B and C in this image there, basically one is B is the like kind of a long track, kind of classic aerial photography kind of geometry. C is the kind of UAS collection where you fly a pattern back and forth, kind of mow the lawn. But they talk about how you can start to reduce some of these doming errors if you introduce radial sort of oblique imagery collects inside. And so this is something you can do when you're programming your UAS flight lines. It's something you can do if you're taking handheld pictures as well. You can also, the Agisoft Metashape has the ability to do lens calibration. If it's a camera that it knows, it has a whole library of lens parameters, and it will apply a lens calibration if it knows what it is, or you can manually calibrate them in your lenses. So that's one example of another way to mitigate this doming problem. So that there's oblique imagery collection, and then the third option is ground reference, is georeferencing. So this is basically putting out targets inside your scene that you can then use to bring in external, GNSS or GPS ground control and use that to flatten it out. And so I think in practice, people use basically a mix of these things, right? So Agisoft's probably going to know your camera and do some kind of lens calibration to begin with. If you do your collection right, you should probably have some oblique images, and then we oftentimes will do external georeferencing for ground control as well. So that's sort of the three approaches. Ramon, do you want to talk through this one since this is your data set?
Yeah, so this is from that, I cited this earlier when I was lecturing on this, Johnson et al. So here we have a place along the San Andreas Fault where there was a prior LiDAR scan, airborne laser scanning. And so then we went out here with our balloon and took pictures. And this was actually using a Nikon DSLR remotely triggered on the balloon platform. And so here you can see the resulting product. And so the left side is an ortho photo. You can see the cars and the road down there on the left. And then the right side is an output that comes from Metashape that shows us kind of how many overlaps there are. And that's what the colors are. So you can see the middle of the model has at least 9 images show the same features on the ground. So many tie points. And then the black dots show the path of the camera as computed from Metashape. So it shows you it's not a very organized flight, but you can see we're trying to walk in a lawnmower pattern. Next slide. And so then here you see the result, and you kind of can zoom in on the right side. We see it's 700 points in the dense cloud per square meter, giving us a 5 centimeter resolution DEM. And so that question came up earlier as far as what ground resolution we could imagine getting. And so there's an example. But then if you go to the next slide, so here's an important comparison. So on the left is airborne laser scanning, a famous data set from 2005. It's called the B4 data set. So it was collected before the next earthquake. And so in some places we're still waiting. But we thought it was amazing at the time, but you can see in detail, it has some issues with sort of swath to swath mismatch. The plane comes back, and there's a little bit of error between the two flights. We get this patterning on there that's called corduroy. And in contrast, the SfM picture on the right side in C is really smooth and higher resolution. But then if you go to the next slide,
Oops, sorry, wrong slide. Whoop.
I guess we don't have, so sorry, just go back. So
Hang on, I think actually I think we like here, right?
there it
This
is.
what you
So
mentioned? Yeah, the order's out of whack.
yeah, so these slides are from that same paper where we compared using kind of what we call a cloud to cloud distance between the B4 LiDAR data set, which is pretty good geometrically, versus the data set we got from SfM from the balloon. And so what you want to look at here is the left side shows the map of distances. And so the redder it is, the farther away the two clouds are. And one of the key things you can see, it's a little bit subtle, but it's more red on the outside. And so that means there's a little bit of a doming problem with the SfM data. And this is with no significant external georeferencing, just some GPS from that camera. And so the histogram in B shows the kind of histogram of distances. And so you can see 90% of the data were within 41 centimeters. So it's not too bad, but we could do better. And so the next slide then shows, and this was the question that came up earlier, was how many points do we need as far as ground control points to improve the error or decrease the error in terms of tying the two together. And so that's shown here where we put out those dots. You can see there's I think 9 of them. And so we georeferenced with external georeferencing that SfM data set. And then now we compare it again against the B4 LiDAR. And so you can see, first of all, the map has a lot less red. And secondly, the map shows maybe meaningful change, like that central sort of yellow zone, which is probably erosion in the channel, because that was from 2005 to 2012 or so. So, there's time for erosion to occur, which is something we do want to capture. And then the histogram shows a real decrease in error. So that's the lesson, is a few ground control points will really beat down the doming and help you out.